everyone. I, Suvarna Mujumdar, Assistant Professor in Electronics and Communication Department of Ajay Kumar Garg Engineering College, welcomes you on a lecture on Architecture of 8086. In previous lecture, we have discussed about the limitations of 8085 and we had also discussed why we are going for 8086 microprocessor, which is a 16-bit processor launched in 1978 and it is having a faster speed, or you can say processing capability as compared to 8085, and also its instruction set is also more powerful. And we have also discussed about the register organization of 8086, that in 8086 we have a general purpose register, special registers which are further classified as pointer and index register, segment register, and control and status register. Now in this lecture I am going to discuss about the architecture of 8086. We have seen that 8086 architecture is basically actually divided into two parts. One is bus interface unit and another part is execution unit. So execution unit consists of arithmetic and logic unit, general purpose registers and pointers and index register, and a status register, that is flag register. To communicate between these two parts, that is execution unit and bus interface unit, it uses internal bus. So internal bus is the medium between the bus interface unit and execution unit. Why this architecture is divided into two parts? Because we already know that whenever microprocessor takes some instruction, when we give an instruction to a microprocessor, that microprocessor first fetch that instruction, then decode it, and then execute it. So by dividing the architecture into two parts, what we are going to do in 8086, that fetching and decoding operation is done at one place and execution is done by execution unit. So while 8086 is executing some instruction, that particular time the bus interface unit is fetching another instruction. This is not possible in 8085. In 8085, microprocessor first fetch the instruction, then decode it and then execute it. And for second instruction, again the cycle will repeat after the execution of first instruction. But in case of 8086 and the advanced microprocessor which we are going to use in today's scenario, all these are using the pipelining architecture. In pipelining architecture, or we can say parallel processing, that fetching and execution and decoding are done simultaneously. Means one part is fetching, another part is executing that instruction. So when microprocessor 8086, the first this pipelining architecture is introduced in this 8086. So this bus interface unit, this generate address on address bus and it goes to the memory unit, and from memory the opcode is fetched, and that fetched opcode and operand all are stored in this instruction queue. So in 8086 we have a 6-byte queue, instruction queue. So at a time it can fetch 6 instructions simultaneously, means one by one, and these instructions are stored here, and the instructions are waiting here for execution. So for example, first instruction is first opcode is stored in 1, second, third, fourth, similar way. So the first opcode is here executed in execution unit, at the same time second instruction should be fetched. So parallel task is going on, and here you can say that that by doing this we can increase the speed also. Processing speed is increased. Now while we have discussed about the register organization, in that we have seen that there are some general purpose register, pointer, index register. So all these registers come under execution unit. And the segment register, CS, DS, SS, ES and the IP. These registers come under bus interface unit. And here the bus control logic, this logic, or you can say this is the place where address is generated, or we can say the address generation circuitry is there. We will see how this address is generated, because microprocessor 8086 has 20 address lines and 16 data lines. But the address that which is stored for reference in microprocessor registers, all the registers are 16-bit. These all registers are 16-bit of size. So from 16-bit we have to generate an address of 20-bit. So how this is going to done? So for that we have an address generation circuitry. And as I told you, this both the unit will work simultaneously. So that's why we can say 8086 need a we can say a faster speed execution also. And one issue is there, that when there is a branching operation, or when we can say when we can we switch from one program to some subroutine program, in that case only this instruction queue has to be empty and it has to be reloaded. Because if because here consecutive instructions are stored, but if we change the transfer from one location, for example our program is running at 3000 location, and here 3000, 3001, 2, 3, 4, 5, 6 like this data is stored. But in between, for example at 3003 we are shifting our program to 4000 or 5000 location, then in that case this further data has to be, or you can say the content of queue should be empty, and it should be reloaded or refreshed with the new location. So this is the only problem. Otherwise this architecture will speed up the execution. Now the next topic that I have to discuss is about the software model of the 8086 microprocessor. So in software model we have how this code segment register can access a memory. As we all know that if 20 address lines are there, so microprocessor 8086 can access 2 raised to power 20, that is approximately you can say 1 megabyte of memory. Okay, so the memory capacity which a microprocessor 8086 can access is 1 megabyte. So this total 1 megabyte of memory we are divided into different segments. This is the external memory address space. So we are divided it into code segment, data segment, stack segment and extra segment. Why we are going to do this? Because by segmentation we can separate the code program, we can separate our data memory, and this separation will help us to give a clear picture to the microprocessor as well as to the programmer also. It is not a jumble. So we go with the segmentation, and the most important part is the in case if we segment it, we can have an address of 16-bit. So if we have to access a code segment, we have to check the data of code segment and for the base address, and for offset we are referring to IP. So to generate a 20-bit address, actually the memory address will be 20-bit, but the that is known as physical address. We will see how this is going to do done by microprocessor, but we have to make a combination so that we can access a 20-bit address of a memory by the combination of like CS IP. With DS we have with DS we can have SI or DI. With SS we can have a combination of SP. So like this we can have a relation between a segment register which will hold the base address, and we will use a pointer or index register to hold the offset. Okay, and we can also access input output device. Now to access input output device, if we are going with IO mapped IO scheme, then in that case we can have 64K, that is 65536 different input output device we can connect to the 8086 microprocessor. And if we are going to go with memory mapped IO configuration, then in case of memory mapped IO, this 2 raised to power 20 address, these memory will be means in that case, this input output device is merged with memory unit and our number of memory locations get reduced. So, to have a proper access to 2 raised to power 20, that is 1 megabyte of memory, we will refer to IO mapped IO configuration. Now, as I told you, we are having a picture of memory segmentation in case of 8086, means total memory is divided into 4 segments. Total memory is of 1 megabyte which a microprocessor can access, and this 1 megabyte of physical memory is divided into 16 segments, each of 64 kilobyte size. Okay, and we are having 4 segment register. So, out of the 16 segment, at a time we are accessing 4 segment in our program. 16-bit content of segment register actually point to the starting location of particular segment. The address of the segment may be assigned from 00 to F00H respectively. To address a specific memory location within the segment, we need a offset address. So, total memory is 1 megabyte. By using segmentation, we will have a 16 segment, each of 64 kilobyte, and out of these 16 segment, at a time we are referring to 4 segment, and the starting address of these 4 segments are stored in CS, DS, ES or SS. These are the register, 16-bit register which will use to hold the starting address of segment. And when we have to address a particular memory location, then we are using offset address. So, for offset to hold the address, offset address, we will either go with pointer register, SP, BP or IP, and index register. Okay, these are used to hold the offset. Okay, take an example that you have in your curriculum, you have to read many subjects, like in every semester you are having 6 theory subjects. So, these 6 theory subjects means total 4 year you are having 6 into 12 into what you can say 4, 48. So, 48 subjects are there. If we check take an example, out of these 48 subjects, each semester you are having 6 subjects. Okay, so your total 48 subjects are divided, like here 1 megabyte memory are divided into 16 segment. So, total your curriculum of 4-year BTech degree program is divided into 48 theory subjects. Out of these 48 theory subjects, every semester you are only having an access to 6 subjects. So, similarly, out of these 16, we are having an access of only 4 segment register, and these 6 subjects which you are studying in particular semester, you are having the books. And in that book, suppose one book is for microprocessor, another book is for Python or data structure or computer organization. Each book you are having an header, that is the name of that book, the first book. So, you can say that is the base address, or you can say the name of that book is stored at some place. So, we can say that the base address, and that book is having a page number 1, 2, 3, 4. So, you are or you can have 5 units suppose. So, you are you have to study about the 3rd unit of microprocessor book. So, microprocessor book, the name of that book is stored in this base, consider as a base address, and the 3rd unit, the 3rd chapter. So, the 3rd chapter is referred by offset address. Okay, so that offset is in the different register. So, in this way you can link that what is memory segmentation. Okay. So there are two types of memory segmentation we are referring. One is non-overlapping segment and one is overlapping segment. Non-overlapping segment means there are two different subjects and you are studying two different subjects, and there are two different units. Overlapping means you are referring two books of that particular subject only. Okay, for example, microprocessor, you are referring two books as a reference books and you are studying in that book. So in that case, you have to keep this mind that, like, if you are referring to different books, then the total CS1 is different, CS2 is different, and you are having different offset IP1 and IP2, and they are not overlapping to each other. You have 64 kilobyte of segment 2 and segment 1. And they are that 64 kilobyte are not overlapping with each other. But if you are referring to one book and in that you are having two subjects or like something like that, then in that case you have having the overlapping. Like this is segment 1 and this is your segment 2. Segment 1 starting address, that is base address, is 1000. So CS1 is having 1000 and CS2 is having 1A00. So in this case, in case of overlapping, might be possible that your code is overlapped because you are using program two code segments which are overlapping to each other. So programmer has to consider this, that if it is using overlapping segment, then it has to write a program in such a way that whenever it is referring to particular code segment, it will not disturb the content of another code segment. So it depends on the programmer which type of scheme it is using, because we have to define this CS1 and CS2. We have to define the modules while accessing the memory. So we can define, we will initialize code segment, we will initialize data segments, stack segment, extra segment, and at the starting of our program when we have to give instruction to the microprocessor. Now the 8086 programming model, programmer's model, or what I can say, whenever we have to program, what all things we have to initialize. So as I told you, we have to initialize all these extra segment, code segment, stack segment, data segment, and instruction pointer. These are the registers that we have to initialize. If we have to perform any arithmetical, logical, or any operation, then we have to use this registers. AX, as I told you, it is an accumulator. BX is base register, CX is counter, DX is data, and these are again the offset address. Flag is used to show the status of after execution of arithmetic and logic. So whenever a programmer has to check all these contents after execution of each or every instruction. So when we write some program of suppose addition, and after addition we have to check what is the content of AH or AL, and if we are going to have an addition between AH and CH, what is the content of CH after addition, if it is going to change or it is remaining same, what is the content of flag, whether carry is generated or not. So this all things are considered as a programmer's model for 8086. Now the most important thing as it is the memory addressing, because in case of 8086 the register which is used to hold the address of memory is 16-bit, but the physical address which are generating is 20 bits. So in case of 8086 we have first thing is that is physical address. As in case of 8086 we have 20 address lines, physical address lines. So we have a physical address of 20 bit. Okay. So how we are going to represent this 20-bit physical address? In hexadecimal form, we are having 5 nibbles to represent 20 bits. So we can write as 3, 2, 4, A, 5. This is one of my physical address. Okay, 3, 2, 4, A, 5. or I can have 2000, 20,000, anything. So I can use 5, 1, 2, 3, 4, 5. 5 digits to represent a 20-bit address. So this is my physical address. Okay, but this physical address is not stored in my microprocessor, because in microprocessor I have a register of 16-bit each. Now how I am going to store my address? What is that address? So I have divided my physical address into two parts. One is known as base address and one is known as offset address. And by the combination of this base and offset address, I can generate my physical address. So what is the relation between this? This base address, it is stored in segment register. This base address is stored in, I can write it, it is 20-bit address. Okay. Base address is stored in segment register. Which is 16-bit. Offset address is stored in either base or index or pointer register, any or both or thrice. We have to check how we can generate. Again, this is 16-bit. Okay, so physical address is 20-bit, but the address which is stored in our microprocessor for reference is base address and offset address. Now, as I told you, in our bus interface unit, we have a address generation circuitry. That address generation circuitry takes the data from the segment register and base index register or a pointer register and generate a 20-bit address. So how it is going to generate? That address generation circuitry consists of a adder circuitry. What it will do? It will just take the content of segment register, multiply it by 10H, or you can say shift it by 4 nibble, multiply by 10H, or you can say shift by 4 nibble, or adds 4 zeros, 1 0, that is nibble, and in this segment register we will add our offset address. Okay, segment this base address is also known as segment address, or you can say here I can write it as base address, which is stored in segment register with offset address, and then we can have a physical address, which is 20-bit. By multiplying 10H, we are already make it as 20-bit, and then we are adding offset address and we can have a physical address. I can take one example and then explain to you. Let us take the base address CS, which is having a value 3000. With CS, we have a combination of IP which is used to hold the offset. So CS base address will be stored. IP is used for offset address. So let's take it as 1234H. Now I have to calculate physical address PA. Now how I am going to do this? So content of CS get multiplied by 10. So my value will be 30,000. Then I will add IP to it. So IP is 1234. So my physical address will be physical address, or another name is machine address. You can have this as a physical address. So this address generation circuitry is there in bus interface unit, which will do this. We have to only take care of that initialization part, that the content of CS and IP must be initialized properly, where we have to refer our memory and we have stored our code. Now in case a microprocessor has to read some data, in that case when microprocessor is reading some operand from memory, then in that case the DS, data segment, the content of data segment and SI will be in picture, and the physical address is generated by having a combination of DS and SI. So for example, suppose our DS is initialized as 4000 and we have SI, we are having 1A00H. Then in this case, our physical address will be generated by having a combination of DS get shifted or multiplied by 10H. So it will become 40,000. Okay. Added with SI. Okay. Just take an example, like if I have written move AH comma SI. When this instruction is given, if this instruction is written at some memory location in memory, so who is pointing to this instruction? CSIP. So CSIP will point to the location where this instruction is written. But when this opcode is fetched, opcode corresponding to this move AH is fetched, decoded. It comes to, microprocessor comes to know that now it has to refer to DSSI. Now after this, the SI is read from here. So this SI, the value of SI and the value of DS is used by address generation circuitry, and this 41A00 address is generated and it is traveling on address bus, and from that particular location the data is picked up by data bus and the data is stored in AH register. Okay, so first CSIP content will travel on address bus, next DSSI content will travel on the address bus. Okay, takes one more example. Suppose push instruction is going to be executed. Okay, push A or push B. Okay, in this case, whenever microprocessor is executing this type of instruction, push or pop, microprocessor is dealing with stack. Stack is that particular memory location which is we use for temporary storage. So push A means temporarily the content of accumulator gets stored at particular location. Now in this case, microprocessor will refer stack segment and stack pointer, okay, to store the content of AH and AL in a memory. So how it is going to done? Now again, microprocessor will check for SS content. Suppose SS is initialized at 6000 and SP is having 2300. Now the physical address is generated. Now physical address will be 623 62300. 1 2 3 4 5. So this is the physical address, and at this physical address the content of AL and HL will be stored. At 623001 content will be stored, AL content, and 62301 second memory location AH will be, because in memory we can only store 8-bit data. Okay, so in this case the address which is traveling on address bus is SS and SP content. But to read this particular instruction, the content of CS and IP will be traveling. Okay. The next that is known as effective address. So, effective address is the address which is stored in your what you can say this SSSP or CSIP. If we are defining like this is our effective address. We are defining our 16-bit address like this: DS, SI, SS, SP. In our program, we have to initialize our address. So, in this way, if we are defining our address, then this is known as effective address. And logical address. So, we can say content which are defining in our program. By this, all these are considered. 16-bit address is our logical address. And effective address is IP, SI, SP, DI content is your effective address. So, this is all about architecture of 8086. Thank you.